I study experimental nuclear physics, mostly looking at the production of new super heavy elements and to expand the periodic table. The best way to describe what we do in experimental nuclear physics is we smash things together at very high speed. So we're using a big accelerator, which we're standing in right now, and we fire a beam of nuclei into a target in this area here. We see what happens, we hope that they stick together, and if they do stick together, we then see what happens with our detectors that surround the experiment. If you get two things to come together and stay together, you have made a new element, as long as there are enough protons in there. What we mostly look at is seeing systems that come together and then actually break apart quite quickly. So we want to work out why that's happening and how to avoid that to make the best reaction choice in the future. So my favourite thing is calcium-48, and basically any target we can possibly find that's heavy. So the heaviest targets that we have is californium, which is 98 protons, element 98. So if you add calcium-48 and californium, which is element 98, you can make element 118. So we've actually done the reactions here. We can't quite make them because it's very difficult for them to stick, but we can see exactly why they don't stick, and that's kind of what I'm looking at in my project. Hopefully in 40 years we can get to element 120. So that'd be two brand new elements put on the periodic table. Lead is the last stable isotope. We want to see something way beyond lead. And hopefully we can reach this so-called island of stability, which is a predicted area where we will find new stable isotopes in a very heavy region of the nuclear chart. At the end of the day, I can just tell my friends I'm smashing things together, seeing what happens, and that's my job. Any data that I look at and that we take here, I am the first person to see like what nature's trying to show us, sort of thing. I think that's a unique thing with research and with physics in general. If you look at the timescales of these reactions as they're coming together and they're sticking together, that's called a zeptosecond. So that's 10 to the minus 21 seconds. Now, if you compare a zeptosecond to a second, it's as if you're comparing the size of the Earth to the size of the observable universe. So it's an incredibly small amount of time, and we can actually see the individual products of the reactions that occur in those sort of timescales. Okay, that's an easy one, table tennis. We play table tennis pretty much for an hour a day, pretty much, well, not an hour a day, but a while a day. At the department we have a table tennis table in the kitchen, and I'd like to say that I'm the self-proclaimed champion of table tennis. I wish, no, if physics hadn't called me, I think I would have gone into history. I would have done a history degree and done that at university. I kind of stumbled into physics. I did a work experience where I went to a radiation therapy machine manufacturer, and I managed to talk to loads of experts in the field, and I was like, oh, okay, now you can kind of get the break through the barrier of where the physics you learn and the physics you can see being in action, and that made me really fall in love with physics. 100 million. Well, I'd buy myself a new car, that'd be good for getting to the work and back. I would try and not go flashy to start with, I'd try and keep humble. But otherwise it would be a Lamborghini Aventador without question. I think $100 million. Try and invest it smartly, probably give some money to the department to make sure we can keep going with the studies, to make sure that we can carry on using this stuff, and probably take my parents on a very expensive holiday somewhere. That's probably the main thing.